So the last section, we're talking about specifically metals. Another example, iron. So if I'm working with iron, I have Fe, Fe, Fe. It's not iron chloride, it's not iron something else. A metal is made up of those atoms, and that's it. What happens is they make these lattices, so they have that nice crystal structure again, and then they have these electrons that move around that make metals the good conductors that they are, which is why we have copper wiring, etc. Here's the questions, here's the vocab. Delocalized, probably the one that might be the newest. So when I have a metal, so pretend this is copper. So if I have copper, here is the nucleus of my copper. So what atomic number is copper? 26? 29. So 29 protons, 29 neutrons. 29 protons, 29 neutrons, positive charge. Copper, 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 copper. Around this copper nucleus, if I have 29 protons, I have how many electrons? 29. So what happens in a metallic bond is these 29 electrons and these 29 electrons are flowing. They're freely moving just around all of those positive electrons. So they don't stay in place quite so much, and therefore they're called a sea of electrons because they can move around from one place to another. So the electron sea model proposes that all the metal atoms in a metallic bond or a metallic solid contribute their electrons to this full sea of electrons, and those electrons can move wherever they want to go. The electrons that are freely moving in a metal, and this is the only place that you'll see this, are called delocalized, which means they don't stay in the same spot. So if I had a sodium chloride bond, my sodium electrons would be here, my chloride electrons would be here, they would be localized. They stay in the same area. In a metal, they are delocalized, they can move around throughout the metal. And because they can move throughout the metal, electric currents can travel throughout that metal very easily. So a metallic bond is simply the attraction between the nucleus, or the metallic cation, and the electrons that surround it. So it is different than an ionic bond. So metals are not ionic, but they do share some properties, specifically the conductive part. They also form lattices, which means they're very patterned. 8 to 12 other atoms typically surround the metal atom. That number's just an example. You don't really need to know that. Also, melting points and boiling points. In a metal, you'll notice that the boiling point is always going to be extremely high, especially compared to the metal melting point. And there is quite a bit of difference. So if I look at lithium compared to copper, another reason we use copper wiring in the house is because its melting point is extremely high. When you put electricity into your light bulb, what happens to your light bulb? It gets hot. Electricity produces heat. Many houses burn down because of faulty wiring. So electricity produces some heat. Copper can hold a lot of heat before it would melt and then not function properly. So like tin, none of your houses are wired with tin metal. That would be an example. Metals are, and these are not vocab words, but I kind of expect you to know these, malleable and ductile. So malleable means you can hammer it into a sheet. So if any of you have put up your own pole shed or helped put up a pole shed, all of those sheets of metal that you buy are malleable. They can be formed into a sheet-like material. Ductile means that they can be drawn out into wires. So copper wire, again, being very common, would be ductile. It can be spread out into a wire. And then these moving electrons, like I said, make metals very good conductors of electricity and heat, both. As the number of electrons increase, so does hardness and strength. So there again, if you go back and look at the table before, you know, if I look at tin, or if I look at aluminum, what is the atomic number of aluminum? Look at copper. What's the atomic number of copper? Which one would be harder? Copper. As the numbers of electrons, if my protons increase, so do my electrons. So basically what this is telling you is the higher the atomic number, the harder that metal is going to be because it has more electrons. And the reason metals are so malleable and flexible is if I hammer it or I put pressure on it, these protons move very easily and I can easily change its shape from one type to another. So I can change it from a round ball and hammer it into a flat sheet or draw it out into a wire. And then, getting towards the end, alloys. And you may not think this is important, but pretty much everything, not everything, but a lot of things that you use are alloys. Your car, the faucets and things in my room are probably alloys. Some of your jewelry is probably alloys. The pots and pans that you cook with. So an alloy is a mixture of elements that has a metallic property. And usually an alloy is a mixture that has at least one metal in it and maybe some other things too. So examples, band instruments, also alloys, stainless steel, brass, cast iron pots and pans. The properties differ from elements they contain. And I thought that it gave an example. Steel, steel is iron mixed with at least one other element. So when you use steel, a lot of times it probably has some carbon in with it as well. And what that does, what do you know about iron? What does iron do very easily? Rusts. You don't want iron to build much stuff because it's going to rust very easily. Where if you use steel, it doesn't rust as easily. So adding other elements to it makes it better. Some properties of iron are still present in your steel. It's still magnetic, but it's much stronger. It doesn't corrode as easy. It's better than plain iron. And then there's two types of alloys. Substitutional is just when atoms substitute or they switch places. So I might have two kinds of metals and they're going to flip back and forth. Interstitial alloys are when you have larger and smaller sized atoms. So if I have, what is an example? Well, even if I use steel that has carbon in it. So if I have a big iron atom and a little carbon atom, interstitial means that these smaller atoms are going to kind of fill in between the larger atoms. And there again, not vocab words, but could possibly show up in a multiple choice question. And here's just some common alloys. So a lot of the, steel being very common, lead shot, gold. I guarantee you if you have gold jewelry, it's most likely not pure gold. Pure gold would be very soft, it would not keep its shape. So the gold jewelry that you buy is an alloy, it has something mixed with it, and it's just a table that shows some common alloys and then what's found inside of it. And the last page is your review. So make sure you know the answers to these questions and the vocab that goes with it. And that's the end of chapter 7.